Hi everyone, welcome to the new topic Electric Field Lesson 1. As you know, we have three main topics in Unit 4. They are further mechanics, fields and particles. Today we are starting with the new topic fields. Electric fields, capacitors, magnetic field and electromagnetic induction are the subtopics that comes under fields. You must be familiar to the term fields in physics. Some of the familiar fields are gravitational fields and magnetic fields. Let us see what is meant by electric field and what are the properties of the same. Dear students, this is from the specification. Important terms we are going to learn in this chapter are electric field, strength of the electric field, types of electric field such as radial field and uniform electric field, Coulomb's law, electric potential due to a point charge, and finally field configurations produced by charges and equipotential lines. These are the objectives of today's lesson. First of all, we have to recall the basic concepts and our basic understanding about charges. The second objective is Coulomb's law, and we could expect 4 different types of questions from this part of the electric field, and I have included those model questions also for you. Students, these are the important facts about charges. As you know, there are two kinds of electric charge, which are positive and negative. Opposite charges attract each other and like charges repel. The electric charge on one electron is equal in magnitude and opposite in sign to charge of one proton. An ion is an atom or molecule that has non-zero total charge due to having unequal number of electrons and protons in it. The SI unit of charge is coulombs. The magnitude of this basic charge, which is the charge of an electron, is 1.6 times 10 to the power minus 19 coulombs. Most often, existing charges are separated from neutral objects to obtain some net charge. Point charge. What does it mean? You can assume a small charged mass. Comparing to the mass of that object, if magnitude of charge on it is much greater, then we can say it is an example for a point charge. That is, it has a finite charge only. It doesn't have any observable mass, or its mass could be ignored. Take another example. We have two masses which are charged. They are separated by a specific distance. Comparing to that distance, if charge on those masses are much greater, then it is also comes under which category? Point charge. Similarly, if you place a point charge in an external electric field, it won't interfere or it won't disturb an external electric field also. Dear students, you probably know electrically charged particles can exert a force on each other even when they are not actually touching. We have learned about two different types of forces in AS level. contact forces and non-contact forces or action at a distance. The electrostatic force of attraction or repulsion between two charges is an example for action at a distance. So we know unlike charges are attracting and like charges are repelling. But we don't know how to calculate the exact size or magnitude of this force. Physicist Charles Coulomb came up with a law which described not only the direction but also the size of the force between charged particles. So basically, uh, we got a law, we got an equation to calculate the exact amount of force acting on the charges which are interacting. The law is called Coulomb's law, obviously, which is named after him. Coulomb's law, which is also called inverse square law in electrostatics. Consider two point charges Q1 and Q2. These two charges are placed in a vacuum. The distance between their centers is r. According to Coulomb's law, the magnitude of the force between these 2 point charges is directly proportional to the product of the charges and inversely proportional to square of the distance between them. Remember, we have to take distance between the centers of the charges. Students, if we write Coulomb's law mathematically, according to the first statement, we write F is directly proportional to product of the charges and is inversely proportional to square of the distance between their centers. Combining these two statements give F is directly proportional to Q1 Q2 over R square. That is F equal to K times Q1 Q2 over R square, where K is a constant of proportionality called Coulomb's constant. We have a separate equation to calculate the value for Coulomb's constant. That is K is equal to 1 over 4 pi epsilon 0. Epsilon 0 is the permittivity of free space, which is 8.85 times 10 to the power minus 12 Fermi per meter. Since these 2 point charges are placed in a vacuum, we have taken permittivity of free space in this equation. If we have placed these two charges in a medium, say in water, then we have to take permittivity of water in this equation. Also remember, permittivity is minimum for free space. So after substituting the value for permittivity of free space here, we get a value for Coulomb's constant, which is equal to 8.99 times 10 to the power 9 Newton meter square per Coulomb square. This value would be given to you in the data sheet. The equation for Coulomb's law also will be provided to you. Remember, F is equal to K times Q1 Q2 over R square, where Q1 and Q2 are 2 point charges which is taken in coulombs. R is the distance between their centers which is taken in meters. F is the force taken in newtons, and K is the constant of proportionality called Coulomb's constant. Dear students, next we are going to discuss about one of the important properties of Coulomb's force. Look at diagram A. We have two charges Q1 and Q2. Both are positive. Q1 pushes Q2 away from it. Force F21 represents the direction of force acting on the charge Q2, which is the action. Due to this, Q2 reciprocate the same. Q2 pushes Q1 away from it. F12 is representing the direction of force exerted by Q2 on Q1, which is the reaction. So technically saying F21 and F12 are Newton's third law pairs. They have equal magnitude but acting in the opposite direction. Whether the magnitude of these two charges are equal or not, the magnitude of force remains the same. Diagram B shows the similar idea, but here they are unlike charges. So Q1 is pulling Q2 towards it, which is the action, and pull of Q2 on Q1 towards it is the reaction force. Part C is also giving us a similar idea. The force between two charged particles depends on what is between them. I mean, in which medium we have placed the point charges. If anything other than empty space comes between them, the force between the charges is reduced. Coulomb's constant K is equal to 1 over 4 pi epsilon 0 for point charges placed in vacuum. We know that permittivity is minimum for free space. If you take any other medium, permittivity would be higher, which will reduce the value for K. If value of K is decreasing, what would happen to the value for F? That also decreases. Sodium chloride easily dissolves in water. How does this happen? Have you ever thought about it? In sodium chloride, electrostatic force helps Na plus and Cl minus ions to make a bond between them. So when you put it into water, these ions are in a medium now. So since the permittivity of water is higher than free space, K value decreases, which would reduce the value for electrostatic force of attraction between the ions. Since the force gets weaker, the ions could be easily separated. And one more important information, when you do the calculation, if you get a minus symbol, it is representing an attractive force, and when you do the calculation, if you are getting a positive number, it is representing a repulsive force. If you use like charges like positive and positive, your final answer will be positive. If you are using negative and negative, your final answer will be positive. So since they are like charges, it is representing a repulsion, and if you are using unlike charges, your final answer will be negative, which is purely representing an attractive force between the charges. Now let's do one sample question. Calculate the force between two point charges of 100 microcoulomb placed 125 cm apart in a vacuum. State what difference it would make to the force calculated if one of the charges was negative, the space between the charges was occupied by air, the space was occupied by paraffin. So look at the equation. This is the equation for Coulomb's law, and in order to calculate the force between 2 point charges we can use Coulomb's law as it is. F is equal to, here is Coulomb's constant, and these are the magnitude of the charges given, 100 microcoulomb, 100 microcoulomb, and here comes the distance between their centers also. As you know, uh, we expect the final answer in SI unit, so it is a must to do the conversion. Microcoulomb should be converted to coulombs. Similarly, centimeters should be converted to meters, and if you substitute those values, the final answer would be 57.5 Newton. Now the second question is asking you, uh, if you change one of the charges to negative, what would happen? What would happen if you change one of the charges to negative? Yeah, right now the charges are like charges, so they are repelling, so instead of repulsion it would be an attraction. And if you fill the space between the charges by air, what's going to happen? There won't be much difference in the force. Okay, there's a slight reduction only, or we can even say no change. The reason is very simple. Permittivity of free space and permittivity of air are almost the same, so that's the reason why force remain the same. And if you keep paraffin, because of its high permittivity, what happens? There would be a large reduction in the magnitude of force. Dear students, as you know, Coulomb's law is an inverse square law. What does it mean? F is directly proportional to 1 over r square. So if distance doubles, what would happen to the force? It gets 4 times smaller. Similarly, if you reduce the distance to half, what would happen to the magnitude of force? It becomes 4 times. We have to discuss about the inverse square characteristics in detail. Look at the diagram. 2 point charges Q1 and Q2 are separated by a distance R1. When they are separated by a distance R1, let's say F1 is the magnitude of the force acting on those charges. Now we are moving Q2 to a new position so that the new distance between the charges is R2. Let it make a force F2 between them. Anyhow, F is directly proportional to 1 over r square. That is, F is equal to a constant times 1 over r square, or F times r square is equal to a constant. So the product of force and square of the distance between the charges will be always a constant. So F1 r1 square is equal to F2 r2 square is equal to F3 r3 square is equal to etc. equal to a constant. So this is how we can verify the inverse square relationship. The product of force and square of the distance between the charges will always remain the same. Dear students, next we are going to discuss about how to verify an inverse square relationship from a given graph. Look at the graph. Force against distance graph. We have a curve, or the graph is a curve, and since this is a graph of electrostatic force against distance, according to the theory, we know that it should be representing an inverse square relationship. So how can we find such a relationship from this graph? To do that, first of all, you can choose two random positions, two random distances r1 and r2, and their corresponding forces also could be found from the graph. If the product of f1 and r1 square and f2 and r2 square is equal to a constant, then the graph obeys an inverse square relationship. Next, we are going to do a model question. We have to uh, demonstrate that f and r obeys an inverse square law. This question carries 4 marks. As I discussed before, we have to find 2 points on this graph and show that the graph is obeying inverse square relation. So I took the first point here and the corresponding force. So F1 R1 square is equal to 115 times 20 square, which is equal to 46,000. So the second position is 30 and the corresponding position it's about 51. So F2 R2 square is equal to 51 square times 30 square, which is equal to 45,900. It's not a must to use the multiplying factors given on both answers for this question. It is not a must. You can use it or you can simply ignore it. Here f1 r1 square and f2 r2 square, both values are approximately equal, which shows that this graph is obeying an inverse square relationship. Students, next I wanted to remind you for basic shapes of the graphs. First of all, the shape of y proportional to x graph. It's a straight line passing through the origin. Y proportional to x square graph is a curve with increasing gradient. Y proportional to 1 over x graph is a curve with decreasing gradient. It's an asymptote. Y proportional 1 over x square graph is also a curve with decreasing gradient. But this time the graph is more closer to the x-axis. You should know how to distinguish y proportional to 1 by x and 1 by x square graph. And I request you all to remember these shapes of the graphs. It will really help you to solve MCQs. Next is electrostatic force against distance graphs. Remember, force and distance, they have an inverse square relationship. F is directly proportional to 1 over r square. So in the first graph, we have force on y axis and 1 over r square on x axis. F and 1 over r square are directly proportional, right? So the graph should be a straight line passing through the origin. In second graph, we have taken force on y-axis and distance on x-axis. So in order to get the force, we have to take reciprocal of square of the physical quantity taken on x-axis. So to get F, we have to find reciprocal of square of this one, which means it is representing y proportional to 1 over x square graph. And what's the shape of 1 over x square graph? A graph with decreasing gradient and very close to the x-axis. And the third graph is force against r square graph. Here on x-axis we have taken r square. So, and to get the force we have to just take reciprocal of what is taken on the x-axis, which means this is a y proportional to 1 by x graph, and this is how the shape of the graph. Now we are going to do another model. This is what we call twin pendulum. Two identical table tennis balls M and N are attached to non-conducting threads and suspended from the point P. Each balls are given same positive charge and they hang as shown in the diagram. Mass of the ball is also given. We have to draw the free body force diagram for M. We have to calculate tension. We have to calculate electrostatic force between the balls. We have to calculate charge on each ball, and we have to say what would happen if charge given to the ball M was greater than charge given to ball N. What are the forces acting on the ball M? Of course, its weight is acting vertically downwards. Since there is a stretched string, some tension force must be acting on it. And look, M and N are identical balls. Both are repelling each other. Ball M makes an angle 35 degrees from the vertical due to the push from N. So the other force acting on the ball M is electrostatic force of repulsion from ball N. So here is the free body force diagram. So the next question is to calculate tension in one of the threads. Both M and N are stationary, which shows that the whole system is in equilibrium. Since M is in equilibrium, it is in horizontal and vertical equilibrium as well. So we can split tension into two components. The vertical component of tension will balance the weight of the pole, and the electrostatic force of repulsion is balanced by the horizontal component of tension also. So to calculate tension, we can use vertical equilibrium, that is P cos 35 is equal to mg. Rearranging the equation and making T subject will give you this answer, 3.2 times 10 to the power minus 2 Newton. Next, to calculate electrostatic force of repulsion between the balls, we can use horizontal equilibrium to solve this question. Electrostatic force of repulsion is equal to T sine theta. If you substitute, you will be getting 1.8 times 10 to the power minus 2 newtons. Next question is to calculate charge on each ball. In second part of this question, we have calculated magnitude of electrostatic force. So to find charge on each of the ball, we can use Coulomb's law. Coulomb's law says F is equal to K times Q1 Q2 over R square, which could be rearranged to make Q square subject. Q square is equal to FR square over K. Remember, both are having equal charges, so Q1 is equal to Q2, which is equal to Q. So Q1 into Q2, it will be Q times Q, which is Q square. Then cross multiplication and rearranging will give us this particular equation, and if you substitute values to this equation, you will be getting 2.92 times 10 to the power minus 7 coulombs. Next question is, state and explain what would have happened if charge given to ball M was greater than charge given to ball N. Right now, M and N are having identical charges and they make equal amount of angle too. So if magnitude of M increases, still both charges would be moving further by an equal amount of angle. Today we had discussed about the Newton's third law pair nature of Coulomb forces. Magnitude of force acting on both charges remain the same. So both balls would move through same angle or distance. Uh, that's it. Now we are going to discuss the last model from this topic. Two protons separated by a distance x experiences a repulsive force F. If the separation is increased to 3h, force between the protons would be. So these are the options. Remember, F is inversely proportional to square of the distance. When distance is r, the corresponding force is F, and now distance increased to 3r. So what's going to happen? They follow inverse square relationship, right? So distance increased by 3, so force will be decreased by square of 3. So the right option is F by 9. We have to follow up activities as usual. Assignment 1 and assignment 2. Please submit both assignments on time. Today's lesson is over. We will continue in lesson 2. Thank you for watching.